Welcome to the problem-solving set on fine structure mapping of viral genes and complementation testing. Problem 1 states that 9 different R2- mutants of the T4 bacteriophage were tested for complementation, and the data revealed 2 complementation groups, 1, 2, 5, and 7, and 3, 4, 8, and 9. The 9 mutants were then used for pairwise infection of B strain E. coli. The progeny were tested for their ability to lyse K strain E. coli, with the results shown below. 0 means that progeny did not produce any plaques. Dash means very few produce plaques. And plus means that many produce plaques. 6 of the mutations are point mutations, while the other 3 are deletions. So I'm just going to highlight some important facts. So through the complementation data, they found 2 different complementation groups. Now remember that each complementation group is a gene. So we know that one gene, say gene 1, has mutants 1, 2, 5, and 7. And gene 2 has mutants 3, 4, 8, and 9. Then what they did and what is shown below, this is the complementation data. And the units that they used are 0, dash, and plus. So 0 means no plaques. And that means that these are the deletions. And I'll tell you why in a second. The dash means a few plaques. And these are from reversions. Now this is important because we know that point mutations can revert. But deletions cannot go through reversion. So the deletions here, this is actually lack of reversion. Okay? And then finally the plus, this is many plaques. So basically it's more than 10 times as many plaques as you would see on the few. And this growth is due to recombination. Okay? So just so we know this is what everything means. So the first thing that we're going to do, and the first part of the question asks to determine which 3 mutations are deletions. So we're going to look through, and we see that through complementation, 3, 6, and 7 do not produce any plaques on this E. coli, which means that they did not revert and they did not recombine, and therefore these are our deletions. So the deletions are mutations 3, 6, and 7. Now it's saying if mutation 9 is in the R2b gene, draw the best genetic map to explain all the data. So I'm going to draw a chromosome because the R2 genes are on the same chromosome. And we can say that this side will be R2a, and then this side can be R2b. And it's saying that gene 9 is in the R2b gene. So we could just put that here for now. We could always move it later if we find that that's not the right place for it. So the way to do this is we're going to use the recombination data to order these mutations with respect to the deletions. So let's look at deletion 6 first. When you look down the column for 6, anything that's indicated by a plus means that it recombined with that mutation. What we're looking for here, we already know that the zeros mean it was because of deletion. But we're going to look for dashes, which means that it didn't recombine, it just, that point mutation reverted. So the mutations that don't recombine with 6 are 1, 4, and then if you look across, also 8. So we know that the deletion is going to span through the mutations of 1, 4, and 8. Now, just to recap, if 9 is in R2b, from the complementation pairs, we also know that 3, 4, and 8 must be in R2b. And therefore R2a must be 1, 2, 5, and 7. Okay. So for here, let's say that this is separation of our two genes. And we know that the deletion 6 does not recombine with mutation 1, 4, or 8. So we know that these must be close to each other. So 1 must be somewhere close to R2b, and then 4 and 8 must be somewhere around here. So I'm just going to draw 4 and 8 right now, like this, and we'll use another mutation to actually order them. So we'll say that deletion 6 is going to be here, spanning all three. Now let's look at mutation 3. Deletion 3, if you look across the column for 3, it does not recombine with 4 or 9. So we know that deletion 3 must span 4 and 9. So if we put this here and say this is deletion 3, then that must mean that 4 is right around here, so that way it's covered by both deletion 6 and deletion 3, and that mutation 8 must be around here. So now that we've ordered these two, I'm going to erase this. And just so you know, I know that I put 9 on the outside before, but the fact that deletion 6 covered 1, 8, and 4, we know that 9 is actually outside of 8 and 4 because it's part of the R2b gene but not part of the 6 deleted region. Now let's look at deletion 7. If you look down the column for 7, we see that it does not recombine with mutation 1, mutation 2, or mutation 5. So we know it's 1, 2, 5, right? 1, 2, 5. So if this is 1 on the right side of R2a, we know that 7 is going to overlap for 1. And it's also going to overlap for 2 and 5. However, because that's the last of our deletions, we can't actually know the order of 2 and 5, and we'll have to do another complementation test for that. So we know that 2 and 5 are to the left of mutation 1 in the R2a gene, but we don't know their exact order. So this would be a genetic map for this complementation data. So you see that 8, 4, 9, and 3 are part of the R2b gene, and 1, 2, 5, and 7 are part of the R2a gene, and then mutation 6 actually spans both genes, and that's how we knew that 1, 8, and 4 were close together. Okay, so this completes this problem. Problem 2. For each of the following data sets, 2 R2 mutants were used for pairwise infection of the B strain of E. coli. The progeny lysate was then plated on E. coli strain K and strain B. The number of plaques were counted and recorded below. Determine the map distance between the mutants in each set. So remember that the only plaques that can grow on K are the recombinants that gave wild type. And the map distance formula for this type of pairwise infection is equal to the number of plaques on K times 2 divided by the number of plaques on the B strain times 100. So let's do A. They saw 4 plaques on strain K, so it's going to be 8 over, and then 2,500 plaques on strain B. So you get 0.32 centimorgans between the two mutants. For B, you see 6 plaques on K, so we're going to do 12 over 10,000 times 100. So for that, you get 0.12 centimorgans apart. And for C, you only see 2 plaques on strain K, so it's going to be 4 over 8,500 on plaque on strain B. So you get 0.047 centimorgans apart. So as you can see, the closer the 2 mutations are linked, the less recombination you're going to have, and therefore the less number of plaques you're going to see on E. coli strain K. Problem 3. 8 different strains of hamster have been isolated, each showing a recessive fur phenotype. For the crosses performed as follows, determine how many different genes are present. The plus symbol indicates wild-type fur, and 0 indicates the recessive phenotype. So this is what's known as complementation testing. And this is to determine how many genes are involved in these mutations. So when you do a complementation, if you do, let's say, strain 1 times strain 2, and they both have a recessive fur phenotype, but their offspring, the complements, have wild-type fur, that means that these mutations, mutation 1 and mutation 2, were on different genes. So here they want to know how many different genes are present. So we want to know which mutations are actually on the same gene. So what we're going to look for, because remember that wild type is symbolized by a plus, we're going to look for complements that yield the recessive phenotype again. So we're looking for the zeros. So if you go across, you see that obviously any of these strains complemented with themselves will not give you a wild-type fur because it's the same mutation. So you're going to have the recessive mutation on both of the genes that you're contributing, and therefore you won't get wild-type. So aside from the selfing, let's look across for A. We see that A complemented with B does not yield the wild-type. So we're going to say that A and B are on the same gene because there's no recombination and they do not revert back to wild type. Now if you look across for B, you don't see any of that. So that makes sense because with these charts, even though it's diagonal like this, basically what this means is that the other side is just a mirror image of what you would see above. So you really only need to show like half of this through the diagonal because there's enough information here. So when you look down at C, you can see that obviously C complemented with itself does not give wild-type fur. But C and E do not give wild-type, and C and G do not give wild-type. So we're going to assume that C, E, and G are on the same gene. And if you want to double check that, you could see that for the E row, again you see it doesn't complement with G, so that makes sense. All the other ones, D, the only one that doesn't complement with is itself, so D is on a separate gene. And the same goes for F, and the same goes for H. So all in all, there are 5 different genes present, and these are the mutations on each of the 5s. So 5 genes. Problem 4. 4 strains, A through D, of pure breeding plants with wrinkled petals are isolated, and a series of crosses gave the following data. A crossed with C gives wrinkled, A crossed with B gives wild-type petals, A crossed with D gives wild-type, B crossed with C gives wild-type, B crossed with D gives wrinkled, and C crossed with D gives wild-type. It says, based on this data, determine the complementation groups for the 4 genes. So this is kind of similar to the previous problem in that strains that are not in the same complementation group will complement each other to give the wild-type phenotype. So what we're looking for is the non-wild-type phenotype. So we're looking for wrinkled. So you see A complemented with C gives wrinkled, and also B complemented with D gives wrinkled. So based on this data, we would say that A and C is in one complementation group, and B and D is in the other complementation group. And to double check, you can see that all of the crosses that yield wild-type petals are between genes of the different complementation groups. So A cross with B, A cross with D, and then B cross with C, and B cross with A, and also C cross with D. So all of those give wild type, so this is definitely, we can say we're confident that these are the two complementation groups. Problem 5. 5 different strains of mutant yeast, all auxotrophic for leucine, were tested for complementation. The resulting diploids were tested for their ability to grow on medium lacking leucine, and the results are shown below. How many different genes did this experiment isolate that are involved in the synthesis of leucine? What are the complementation groups? Plus indicates growth and minus indicates no growth. So again, this is going along with the theme of finding complementation groups. So remember that mutants in the same complementation group, when crossed with each other, do not give wild type. They still give no growth. So when we're looking for complementation groups, we're looking for complements that do not give any growth. So let's just go through and circle them. Obviously, as I said before, when any of the mutants are crossed with themselves, they're not going to give wild type because they have the mutation in the same spot. So all this diagonal from 1 down to 5 crossed with 5, we're just going to ignore that for now. So if you look down the 1 column, you see that 1 complemented with 5 does not give any growth. Okay, and then you also see, if you look down the 3 column, you see that 3 complemented with 4 does not give any growth. And that's the same as this, 3 and 4. And then again, here's 5 and 1. So we know that the complementation groups for this are going to be 1 and 5, because they do not complement each other, 3 and 4, and then 2 is by itself. So remember that each complementation group equals a gene. And the reason why mutations within the same gene don't complement each other is because it's very hard for recombination to happen between a single gene, just because it's so close together, obviously. So we have 3 genes involved in the synthesis of leucine, and these are the complementation groups. So again, a complementation group, so we could say mutations in the same complementation group, which remember is just a gene, do not give you wild type. So when you're looking for complementation groups, look for the mutation phenotype. So I hope this is getting easier. It's something you have to just keep doing problems to get used to finding complementation groups. Problem 6. The map below shows 4 deletions involving the T4 phage gene R2b, where the lines indicate the deleted region. 4 point mutations A through D in R2b are tested against these deletions for their ability to give wild-type recombinants, indicated as plus. Based on the results shown below, determine the order of point mutations in the R2b gene. Okay, so it's very important that you remember that the lines are indicating the deleted region. So when you're crossing a point mutation against the deletion, and you're looking for recombination or wild type for recombination. So when you see a plus, that means that that mutant must be in the area of the deletion that isn't deleted, because obviously you can't recombine with a deleted portion. So let's go through. We say that mutation A only recombines with deletion 3, which means that it must be in an area of deletion 3 that wasn't deleted, but in an area that the other 3 were deleted. So what area has deletion portions in 1, 2, and 4, but not 3? If you see, I'm just going to do it with 2 lines. And you could see that point mutation A would be somewhere around here, because there's a deleted section in that part from deletion 1. there's a deleted section in that part from deletion 2, and there's a deleted section from deletion 4 right there. Okay, so now let's look at B. B only recombines with deletion 1, so it must be in a spot that is not deleted for deletion 1, but is deleted for the other 3. Now remember, again, the lines are what is deleted. So if you look at the right, these two horizontal lines, vertical lines, I'm sorry, are areas where there's deleted section of 2, 3, and 4, but not 1. So this is going to be around where the mutation B is. Now C recombines to form wild type with deletion 1 and also deletion 3. So we're looking for an area that isn't deleted for 1 or 3, but is deleted for 2 and 4. And that would be somewhere in this region. So this is going to be C, because as you can see, there's a deleted portion of 4 and a deletion portion of 2, but there's still the chromosomes left from 1 and 3. Now finally for D, it recombines with deletion 2 and 3, but not with 1 and 4. So we're looking for a spot that isn't deleted for 2 and 3, but is for 1 and 4. So if you look, that would be here. Because it is deleted for 1 and 4, and there's still chromosome segment there for 2 and 3. So based on these results, the order of point mutations in the R2B gene is going to be D, A, C, B. I'll see you at the next session.